Hello, it's Matteo Buzzegoli from Florence University. Welcome to this video poster. The magnetic moment is a familiar concept in physics. We know that the magnetic moment of a particle is proportional to the spin of that particle. The coupling of the magnetic moment of a particle or an atom with an external magnetic field can be detected through the Zeeman effect. The magnetic moment of a particle can be determined with great precision by measuring the Larmor frequency of that particle when embedded in a known magnetic field. From now on, when I say magnetic moment, I refer to the adimensional g-factor that gives the magnitude of the proper magnetic moment. Similarly, in a rotating medium, the spin of a particle couples with the external rotation. In analogy with the magnetic moment, the g-factor related to rotation is called the gravity-magnetic moment. We can explore the similarities between magnetic and gravity-magnetic moment by considering the Dirac equation in an external magnetic field and using rotating coordinates. D is the covariant derivative and includes the magnetic field in the equation, while the non-inertial effects of rotation are contained in the spin connection gamma. By applying 2 times the Dirac equation to the field psi, we eventually obtain the second-order Dirac equation, where the coupling between spin and magnetic moment and spin and rotation is quite clear. If we do not include quantum field theory effects, the Dirac equation predicts magnetic moment equals to 2, and the gravity-magnetic moment equals to 1. We already have direct evidence of the spin-rotation coupling. This was accomplished by measuring the Zeeman splitting of the stationary state of 2 isotopes of mercury atoms into different magnetic field orientations, one parallel to the rotation axis of the Earth and one anti-parallel. The measurements are consistent with the gravity-magnetic moment of 1. The spin-rotation coupling is also the basis of the Barnett and the Einstein-Dehaas effects. Barnett effect is the magnetization of an uncharged body by the application of mechanical rotation. On the reverse, Einstein-Dehaas effect refers to the mechanical rotation induced by magnetizing a ferromagnet. More recently, evidence for spin-rotation coupling was found in relativistic heavy-ion collisions. Non-central collisions generate a quark-gluon plasma with a very high vorticity. The spin of the particles, due to spin-rotation coupling, tends to align along the angular momentum of the system. The higher the vorticity, the higher the number of particles with a spin aligned to the angular momentum of the system. This is confirmed by measuring the polarization of particles, such as the lambda hyperons, emitted by the quark-gluon plasma. Another effect in relativistic fluids, and deeply related to polarization, is the axial vortical effect, or AVE. Consider a spin 1/2 Dirac particle at thermal equilibrium in a rotating medium, and consider the axial current of such particle. It's found that an average axial charge flow is induced along the rotation of the medium. In a non-interacting theory, the AVE conductivity WA is given by this formula, where NF is the Fermi-Dirac distribution function. For a massless field, the integration yields to this expression, which was also derived in several different approaches. In general, for any microscopic theory, the AVE conductivity can be obtained by this Kubo formula. This formula involves the thermal average of the product between the stress energy tensor and the axial current, or, in terms of Feynman diagrams, is obtained from this diagram. The leading 3-level diagram gives the result shown before. For massless quantum electrodynamics, or QED, the first loop's diagrams were also considered. They found that only this diagram can contribute to the AVE, and the result is the following, where E is the QED coupling constant. Now, I want to give a different interpretation of this diagram, where the radiative corrections to AVE in QED are driven by the interaction of the graviton with the photon cloud surrounding the fermion. Indeed, we may understand the coupling between the chirality of fermions and the rotation of the medium induced by this diagram as follows. Suppose the lower blue fermion line inside the loop has a right chirality. Then, it couples more effectively to photons having a polarization parallel to the fermion spin. Following the loop in the diagram, those photons then interact with the rotation of the medium, that is the stress energy tensor, forcing their polarization to rotate. So, when they couple to the fermion in the loop again, they can induce the chirality flip of the fermion and transform it into a left-handed one. Note that this requires the presence of photons in the rotating fluid, which, in thermal equilibrium, implies a finite temperature. At zero temperature, the photon cloud is part of the coherent state of a charged fermion, and thus rotates together with it. Instead, at finite temperature, the thermal bath possesses its own photons, and mixing between these photons and the photons that form the coherent cloud of the fermion can cause the rotation of the fermion's polarization. In the work I am presenting, we have shown that, number 1, the gravitomagnetic moment of a Dirac massive particle indeed receives radiative corrections if the particle is at thermal equilibrium. We computed the anomalous gravitomagnetic moment, or AGM, for QED, and we found that it is given by this expression. Number 2, the radiative correction of the AVE for a massive field is connected to the anomalous gravitomagnetic moment, as suggested by the interpretation I gave to the previous diagram. As I will show later, we obtained this formula for the IVA conductivity WA. Here, the effects of interactions are gathered together into g omega of k, which is the momentum-dependent gravitomagnetic moment. If g omega is equals to 1, which means if g omega is not anomalous, then the value for WA is the non-interacting one. Instead, WA has radiative corrections if and only if g omega is anomalous. Let's start with the AGM first. You may be surprised to hear that the gravitomagnetic moment is anomalous, as it has been shown that the Einstein equivalence principle forbids the appearance of an anomalous spin-rotation coupling. In the language of quantum field theory, the equivalence principle is translated into the Lorentz invariance of the local coupling of gravitational fields to the stress-energy tensor, and the non-anomalous nature of gravitomagnetic moment is obtained as a low-energy theorem. So, why bother listening to me? Because I am discussing a particle at a thermal equilibrium in a medium, and the presence of a thermal bath breaks the Lorentz invariance of the vacuum. In these settings, the premises of the equivalence principle no longer apply, and the equivalence principle can be violated. Just think that because of the presence of thermal bath, we have a preferred frame of reference, and we can discern if the system is under acceleration or under the effect of a gravitational field by making measurements in reference to the thermal bath. The breaking of weak equivalence principle at finite temperature has been already demonstrated in these papers. Remind what I said about this diagram? It can only be non-vanishing at finite temperature, because we need the photons from the thermal bath. This is another way to see it. To show you how we determined the gravitomagnetic moment, I once again make a comparison with the magnetic moment. The interaction Lagrangian is the scalar product between the electric current J and the gauge field A. The anomalous magnetic moment is given by a form factor of the matrix elements of the electric current. For the gravitomagnetic moment, the interaction Lagrangian in the weak gravitational field limit is the contraction of the stress-energy tensor with h, the deviation from the Minkowski metric, and the gravitomagnetic moment will be given by the form factor of the stress-energy tensor. Notice that this decomposition is made at finite temperature, and the covariance is broken by the presence of the thermal bath velocity, denoted with U. The expression for the gravitomagnetic moment is obtained with scattering theory. The rotation of our system is introduced with a metric of rotating coordinates. We then compute the scattering amplitude A. The result is compared with the amplitude coming from a potential containing the spin rotation coupling. We found that the gravitomagnetic moment is given by this combination of form factors. As an example, we computed the form factors for QED at finite temperature by renormalizing the stress-energy tensor at one loop and at first order of momentum transfer. The final result is this one, which I showed you before. Let's see how this is related to the axial vortical effect. We start from its Kubo formula. The basic idea is that for massive field, the internal fermion lines in this figure are essentially one-particle states, and the left part of the diagram with the stress-energy tensor, including the gray blob, is the renormalization of the stress-energy tensor that we have considered for the gravitomagnetic moment. With explicit calculations, we found that indeed only the parts that recreate the gravitomagnetic moment contribute to this diagram. Formally, we evaluated the AVE conductivity by writing the stress-energy tensor and the axial current operators as a sum of multi-particle states. In this way, the effects of interactions are included in the matrix elements of the stress-energy tensor and the axial current. Carrying out the calculation in the limit of mass m larger than the temperature T, we eventually obtain this formula, where we recognize the specific combination of the form factors of the stress-energy tensor as the gravitomagnetic moment g omega. Let me stress that this equation holds in the large mass limit, where we can factorize long and short distance contributions. The effect of interaction above some energy scale, short distances, are contained in the form factors, which we renormalize at the finite temperature and result in the gravitomagnetic moment. The low energy contributions, large distances, are collected into the thermal averages of one-particle states, which correspond to an expansion in T over m. I conclude by showing you the summary of the main points. Thank you for listening, and a special thanks to all the Cortona Young 2021 organizer. Ciao!